They have to go to this one.
Yes.
Okay, it is 4:30 now, so I guess we will begin. Okay, so welcome to the computer security seminar from Purdue University. Today's speaker is Dennis Fetterly from Microsoft, and he will speak on using statistical analysis to locate spam web pages. Hope he tells us why he wants to locate spam web pages. Okay, Dennis.
Hi. As Sam said, my name is Dennis Fetterly. I'm from Microsoft Research's Silicon Valley Lab, which is located in Mountain View, California. And I'm going to talk today about work I've been doing with Marc, Manasse, and Marc Najork on using statistical analysis to locate spam web pages. First, to motivate the rest of the discussion, I wanted to show you some example spam web pages. So in this first example, you can see that the page consists solely of hyperlinks. And the target for each one of these hyperlinks is the current URL with the anchor text appended to it. So you're creating a deep structure. And if you follow one of these links, the first link is the target of this particular piece of web spam. And the 8 links beyond that go to pages similar to the one that we just came from, creating an infinite URL space. As you can see toward the bottom of the page, there are a jumble of keywords that presumably this the author of this page believes would be likely query terms, and thus make this page likely to be returned. If you look at a slightly different example, you have what was at one time a coherent block of text that has keywords stuffed down into it, and then you have keyword link pairs at the bottom. And in a final example, you have a random series of words and then a number of links. One thing common among all of these pages is they are useless to a human surfer. They are only useful to a crawler who would actually be trying to extract the links and then follow them. So here's some definitions that I'll use in the remainder of the talk. Web spam is web pages that are designed to cause search engines to misdirect traffic from search results to the target site. And there's a few different types of web spam. There's keyword stuffing, whereas we've seen you have just a set of random keywords but no actual content in a page. There's link spam, which is a technique for fooling PageRank or other link-based ranking algorithms, where you create a large number of pages, all of which point to the target site. Or there's a game. You can try and game the search engine's ranking function by publishing many different similar pages with slight variations, hoping that at least one of them will rank highly. And it's important to note that web spam is not email spam. Instead of the target being the end user who is being exhorted to buy something, the target is a search engine where you want to increase the ranking of whatever the target site is. And sometimes deciding whether or not a page is spam is a judgment call, because it might have some small bit of useful content and then say 2,000 or 3,000 links off to useless pages. And so you have to decide whether or not that's a useful page or not. The increasing importance of search engines has given rise to an industry of search engine optimizers. These are folks who help a commercial website rank highly for queries that are relevant to that site's business. They're commonly known as SEOs. And our project is to use statistical techniques to detect web spam, or at least a reasonable fraction of it. Web spam is a problem for search engines because it pollutes the corpus. As we've seen, many sites create an infinite URL space, so you get an infinite number of pages, and your index is finite sized. More importantly, as your index gets larger, your cost per query increases as well. So you want to get rid of these junk pages and replace them with useful pages. And they distort the relevance of the results you return because of the fluctuations in ranking that they cause. And finally, these pages all burn crawling bandwidth because they're not pages that you would actually ever want to return to a user in a result query, so you don't actually want to crawl them either. We began this investigation into web spam as a result of one of the things that we discovered while doing a study on how much web pages change week over week about 18 months ago now. And we discovered a strange anomaly in Germany where pages were 9 times as likely to undergo significant change as pages on the web as a whole. And we traced most of this anomaly down to a single IP address where the pages were changing on every single reload. In our data set, we had more than 116,000 different hosts that mapped to this one IP address and more than 1 million pages, each one of which had been randomly generated at crawl time. So these pages changed too quickly compared to pages on the web as a whole, but if you looked at the other properties of them, they looked fairly normal. They had appropriate distributions of non-markup words in them, appropriate numbers of links that had the right distribution, and they were grammatically well-formed sentences, but if you put these sentences together into paragraphs, then they didn't make sense anymore. So if we could find this site because it displayed a statistical anomaly, could we use the same sort of statistical analysis to find others? And if so, what types of anomalies should we be looking for? Our initial hypothesis was that we would expect to find spam around any metric that a search engine would use for ranking, since people would have to have some reason for spamming a search engine. Here's a list of properties that we examined. We looked at the URL itself. As we saw in the first example, if you create a deep URL tree, you would expect that a spam URL from a spam site might have more path components in it, or thus more slashes. Might also be strange because it would have extra digits or dashes. And we applied the same techniques to the hostname component of the URL itself, as well as looking at the results of performing DNS resolutions on all of the hostnames in our set. A metric called the host machine ratio, which uses that information, which I will define shortly. The link structure that is induced by these pages, including the in degree, or the number of pages that link to a particular page, and the out degree, or the number of links that are contained in that page. And the syntactic content, such as the number of non-markup words or the length of the content in bytes. We also looked, as I mentioned, at how fast this content evolved over time, as well as perform a clustering of near duplicate documents. And just by looking at these properties, we can identify 75% of the spam that we expect exists in our collection. So about our collection. We have 2 different data sets. The first, which I'll refer to as DS1, consists of 150 million URLs, which we downloaded each week for 11 weeks. The initial crawl was a breadth-first search crawl starting at the Yahoo homepage. And the remaining weeks were crawled exactly that same set of URLs. That crawl took place between November of 2002 and February of 2003. The second data set, or DS2, was the result of a single breadth-first search crawl starting at Yahoo, and it contained 429 million HTML pages, as well as we followed 38 million HTTP redirects. This took place between July and September of 2002. For the DS1 crawl, we retained the following information: the URL, the start time of the download, the fetch duration, the length of the document in bytes, the number of non-markup words contained in the document, and an entire document checksum, as well as a vector of 84 features which identified the text of the document, any HTTP status code or error condition that existed, and we retained the full text of 0.1% of these pages that we downloaded for future analysis. It came in handy when we wanted to determine how much spam was in this collection, because we took a random sample of 750 of these pages and determined that there's about 8.1% with a confidence interval of 2 worth of spam in this collection. For DS2, we retained the URL, the URLs of each link that was contained in the page, as well as the source and destination URL for each HTTP redirect that we followed. And since we hadn't retained pages, we had to inspect current versions of these URLs to try and determine whether or not they were spam. And out of a random sample of 1,000 pages, 465 of them could not be downloaded or contain no text, and 6.9% of the remainder were spam. That statistic has a confidence interval of 2.2. The first property we looked at was the URL itself, as I mentioned. So you might expect, as we did, that a dynamic site that was kind of built with a deep tree would have, as I mentioned, kind of long URL paths. However, we didn't find any correlation between any properties of the complete URL and spam. However, when we applied the same technique to just the host component of the URL, we actually did find that correlation. And so synthetic host names do look different. They're longer, they have more dots in them, more dashes, and more digits. This is easy for a site to accomplish because, as you may be aware, you can create a wildcard DNS record. So any record that doesn't have a more specific pointer can be resolved to a specific address. As an example, at the time the slide was created, the highriskmortgage.com domain, if you tried to look up any host name in that, it would resolve to 65.83.94.42. And the reason that sites do this is there's a piece of SEO folklore that says that if a component of your host name exists as one of the query terms, then your result will be ranked higher. And so they try and game the system. As you can see, there's 4 example host names there that are very long. And in 3 of them, it's easy to see what query that particular host name is trying to game. There's also a graph that shows you the histogram of the hostname length in characters for all the hosts that were in DS2. And the blue box identifies the hosts that we've identified as potential spam candidates. And that's a convention that will be used in the remainder of the slide. So this technique flags 0.17% of all pages in our collection as spam. A side effect of SEOs creating all of these host names that point to a single IP address is we can look at how many host names resolve to a particular IP address as an indicator of spam. This graph shows you the histogram of the number of host names that map to a single IP address. And if you look in the far right corner, you can see that there's nearly 9 million host names that map to that one particular IP address. And in this case, they've taken words from the Italian dictionary and created host names for them. And if you try and connect to any of those host names, you will just get a redirect back to their main domain. So this technique is extremely effective. It flags 3.46% of all pages in our collection as spam. However, it also has a high false positive rate, which comes from sites, typically blog sites and things like that, where you create a separate host name for every user that has an account on the system in order to shorten the URL length. You can mitigate this with a short whitelist of known good sites. There's another piece of SEO folklore that says that a remote link should be valued more than a local link. And this makes sense if you think about the endorsement power that links have. If a site links to some other site, it says more about the other site than if that same site linked to itself. So in order to try and flag pages that have many links that appear to be remote but are actually local once you have performed DNS resolution, we define the host machine ratio metric, where we define the host machine ratio of a particular page P to be the size of the set of host names referred to by links in that page divided by the size of the set of distinct IP addresses that those host names resolve to. And then compute the host machine ratio of the machine is the average host machine ratio of all of the pages that are served by that machine. And we found that machines that have high host machine ratios are very likely to be spam sites. Again, this plot shows you the average host machine ratio for all the machines in our data set. And the blue rectangle identifies those of which that are spam candidates. So this technique flags 1.69% of all pages as spam. Looking a little deeper at the link structure, we plot the in-degree and out-degree distributions. As previous work has shown, these distributions are Zipfians, and the outliers are predominantly spam. So in the upper plot, which is a plot of the in degree, if you see the point that the arrow is indicating, that's the point that has in degree 1001. That has about 185 times as many URLs that have exactly that in degree as the distribution suggests that it should, which is fairly clearly spam. And there's some sample URLs from that in degree. If you look at the lower plot, which shows you the out degree, it's not the outlier that's indicated by the red arrow is not as significant. It only has 100 times as many URLs as are indicated that it should have by the distribution. And as a matter of fact, out of the URLs, all of the ones that are not expected by the exactly the number that's not expected by the distribution comes from one particular domain, which again is a clear indicator that this is a spam site. So the in-degree technique flags 0.2% of all pages in our collection as spam, while the out-degree technique flags 0.05%. Looking at the syntactic content, such as the number of non-markup words or the content length in bytes, we observe that normal websites have a variety of pages on them. And so the size and word count distributions are typically Gaussian, and they have a non-zero variance. However, some spam sites generate very templatic pages, often where they've taken a particular block of text and stomped 2 keywords and a link down at kind of predetermined offsets within a page. And these sites show near zero variance in size and word count distributions. So the exception to this actually turns out to be something called soft error pages. A soft error page is a page that's returned with an HTTP result code of 200, which means OK. But it actually, the text on the page indicates that it should have had some other return code, such as a 401 or you're not authorized to view this page, or a 404 document not found. I'm sure everyone has gone to a site and seen a page that says, this document couldn't be found. Please start over at our homepage or search for it. These pages are also not useful for a search engine to include because they only contain this error message. And a good example of this is the site www.protein.com, which contains protein sequence information that various scientists deep link into all of the time. However, if you're not a subscriber, all you get back is a login page, whereas if you are a subscriber, you get the actual sequence data. So this technique flags 0.21% of all pages in our collection as spam. As I mentioned at the beginning, the reason we began this investigation was because we found a site in Germany where the pages were evolving too fast. So as it turns out, there's many other spam sites that are generating web pages on the fly, and the content that's returned may not have any relation to the URL that's requested. So if you request the same URL multiple times, you will get different content each time. And a search engine can detect this by measuring page evolution. So this plot shows you the average number of matching features per document from 1 week to the next, where 0 on the right-hand side means the document completely changed, and 84, which is the maximum value on the left-hand side, means there was no detected text change. It's a probabilistic sampling method, so there is a slight chance that there was actually a change that just wasn't detected. And as you can see, for the majority of IP addresses, most pages don't undergo significant change. However, if you look in the blue band on the right, you can see that there are a number of IP addresses where every document, on average, undergoes complete change from week to week. And in fact, I've drawn an orange circle around the IP address in the far upper right that was the German spammer I mentioned at the beginning. You might think that sites such as news sites or discussion groups would actually be identified by this metric, but that's not the case because we were crawling a fixed set of URLs, and news sites typically only change their front page, and all of the links to the articles are actually, the article itself doesn't change, and so that article is always available at that URL. And for discussion groups and things like that, there's often enough navigation information on the page so that it doesn't show up as a complete change, just as a significant change. So this technique flags 0.93% of all pages in our collection as spam. We can also use these features to cluster near duplicate pages into equivalence classes in order to identify content that's been published under, similar content that's been published under many different URLs, even across many different IP addresses. And the largest clusters are almost exclusively spam. However, you will notice that there's another set of outliers around cluster size 100. So this is legitimate content replication for things like the PHP documentation, MySQL database documentation, the Linux documentation project, and all of the mirrors of the 2Cow software download site. So this technique flags 1.38% of all documents as spam. And here's a table of the 20 largest clusters. One, in the left-hand column, you have the number of URLs in the cluster, followed by the number of hosts that were symbolic host names that were contained within those URLs. The third column is the number of machines, where the number in parentheses is the number of host names that we couldn't resolve, since we unfortunately did not save the DNS resolution that we did at crawl time, and thus had to re-resolve all of the host names that were contained in our data set. It's followed by a description and a representative URL. Some of the interesting things to look at here are the ratio between the number of hosts in a cluster and the number of machines. If you have nearly 1 million URLs and 6,000 host names, but only 3 IP addresses, it's likely that you're publishing duplicate content as opposed to having a legitimate mirror of content. However, if you have something like the next size, where you have a little over 300,000 URLs in a cluster on 335 host names and about 200 IP addresses, that's probably legitimate content replication. And the only other example in here that's particularly interesting is the cluster with a little less than 100,000 pages in it, where the content of the page is nothing but untitled document in the title. So this is some HTML authoring tool that saves pages, and it turns out that a number of people have obviously created empty pages and then had links to them. In this slide, we show you how effective each of these techniques are. The red bar shows the number of pages that were correctly identified as spam out of the flagged candidates. The yellow bar is a soft error page. White is no text. And green is a false positive. As I mentioned earlier, you can see that the hostname resolution technique has the highest false positive rate of any of them. And the word count variance technique is very accurate or precise. However, if you scale each one of these bars by the number of pages that they flag, you will see that even if you address the issues that are in the hostname resolution technique by using a whitelist, then that technique is far more effective than the word count variance. It's also important to note that the character of pages that you download over the life of the crawl is going to change. Our data sets, as I mentioned, were both collected using breadth-first search crawls starting at the Yahoo homepage. And previous work has shown that the page quality, or more precisely, average page rank, will decrease as the crawl moves forward, which makes sense because high-quality sites are going to be well-connected and you're going to discover them early in the crawl, where later on the crawler can be dominated by large or infinite sites. So these two graphs show you the percentage of spam candidates flagged over the progression of the crawl for DS2 using both the hostname properties technique and the number of host names per IP address as a predictor. And as you can see, they both flag an increasing percentage of pages as spam as the crawl continues. We believe that this is a good sanity check for any proposed metrics for identifying spam pages. In conclusion, we have identified a number of properties that can be used to flag spam web pages. We found that 8.1% approximately of pages in our collection are web spam. And applying all of these techniques in concert to dataset 1, where we had the retained pages, we can flag 4.96% of these. We expect that if we had link information, we could flag an additional 1.7% of these pages, which would get us to about 75% of the spam pages that we expect exist in our collection. However, 14% of these pages are actually good pages that you wouldn't want to flag as spam web pages. Again, mostly from the hostname resolution technique. So some other interesting things that could be done in this area are to use semantic techniques to determine if the actual words on a page could be used to classify a page as spam or not. And we've actually completed this work with the assistance of a summer intern we had this summer, and we intend on publishing it in the near future. And we also would like to benchmark each of these techniques both individually and combined in order to determine their effectiveness on a data set where we had both link information and the full text of each page, as well as the DNS resolution from crawl time. And if you're interested in more information, we have a project webpage, which unfortunately isn't as up to date as it should be at the moment, but the URL is on the slides. Thank you.
With that many slashes in the URL, do you think you'd be flagged as spam there?
Well, if that correlation existed, that's not a particularly deep tree. If we had a host name such as this dot is dot, an example of why web spam is bad, .research.microsoft.com, I would expect that to be flagged as spam.
As you come up with a list of pages, like presumably you could crawl over the internet and find all these, is there anything legally you can do as far as saying, hey, these guys are just putting this up for the sole sake of spamming people, which makes everyone's life miserable, stop them?
Well, if you run a search engine, you can penalize them in a number of ways. You can reduce the ranking that their results have and yet still leave them in your index. You could completely remove them from your index, or you could not crawl any links they contain. Those would all be reasonable approaches. But as far as publishing that information, I think that gets sticky from a legal standpoint. But I'm not a lawyer.
Do you work with Google or Yahoo or any of the other various search engines showing them this?
We published this work at the workshop on the web and databases last June in Paris. So it's in the body of scientific knowledge. There's actually a full paper that's linked to on the project webpage that has results.
And then, this is kind of off-the-wall question, but do you think that, I know at one point the Bush administration was thinking about making, I'll let you start. Part of an issue that a lot of people are having is filtering out pornography so that on like public machines and stuff like that. Do you think, because I noticed that on the webpage you had a number of different, one of your categories was pornography. Can this technology possibly be adapted or used to identify pornography sites as well?
It could be potentially a component of that, but it would be fairly easy if you were running said pornography site to not violate any of the properties that we listed here. And from that aspect, it wouldn't truly identify pornography as it would identify people who are trying to artificially inflate the linking of their pornography site. There's actually a number of those examples did happen to be pornography. I kind of kept a tally on the side when I was doing a fair amount of that sampling because I expected that if most of that would be pornography. There's actually a fair amount of spam that's not pornography that exists. It just didn't happen to be in the list of the largest clusters. There was one. There was a health food store where the proprietor, it was a multi-level marketing type scheme where for some amount of money, they would sell you a website, and the only thing that differentiated your website from someone else's website is that it had your name on the top of it. So I think he was excellent.
Are any of these techniques used in the new MSN search that was just released?
We've communicated this to the MSN folks and talked to them, but I can't comment on product details. So.
What's the largest spam content you have?
What do you mean by largest spam content?
Whether it's pornography or multi-level marketing, or what's like the most common spam content?
Pornography has on the order of 2/3 in our collection. I mean, this is, you know, that's out of a sample of 150 million pages. But, I mean, that's of the spam, not total.
Do you have your data sets are about 2 or 3 years old? If you had something recent, what would you expect the trends to be?
I would expect there to be a higher prevalence of spam.
And do you think, is there a way to know how successful the spammers consider these techniques to be? Are they making money with this? Are they able to sell this? Or are they just implement it?
I believe SEOs make a fair amount of money. I don't know if presumably it works for the website that hires them, or else they wouldn't be paying the amount of money that they are.
Is there any connection between spam and where the server is physically located? Are these like offshore sites? Or?
No. I've looked at a small sample using kind of routing information. So, and it's fairly well distributed.
You mentioned semantic approaches. What semantic methods or methodologies are you looking at right now?
I unfortunately can't talk about that yet. Sorry.
We'll read about that in a future paper.
Yes.
That's right. Where would you draw the line between something that's above board, legitimate things someone can do to make their page visible, and these sort of things?
Well, I think it's easy. It's hard to draw specifically where the line is. It's easy to come up with examples that I've seen that are completely overboard. There was a particular site that put a random number of hyperlinks at the bottom of each page, and by at the bottom I mean outside the closing /HTML. So not correct HTML, and put between 800 and 3,000 links at the bottom of each one of those pages, where the anchor text was an asterisk, and only an asterisk, and they pointed off to various places. And they were smart in that they had a varying number of them. And so a HTML parser that's looking for correct structure wouldn't necessarily see these, but a scanner that is just looking for tags, such as a link extractor that's built into a crawler, would extract them. And so, for example, I would consider that over the line, even though there was actually some content on that page. I mean, they're clearly trying to inflate their ranking by creating links that aren't useful to a human. So it's harder to kind of draw the line specifically.
Would you agree that there's more spam today than like a year or 2 years ago?
On the web? Yes.
Do you have any numerical data or some kind of idea of how fast is it growing? Is it linear, exponential?
So I only have a little data,
Right.
but what I do have would suggest that it's more linear. As a percentage. So, but.
How about correlation between like spam sites and like pop-up ads?
I haven't done that. Again, we mainly for speed, we're trying to avoid doing things where we actually had to parse the page, other than to do things like link extraction. Those types of things become very expensive per page, and with 150 million pages. So.
Do you think is there potentially a link between these pages that you've identified and spam that's coming from the email?
I wouldn't think so. Most of these pages really exist for a crawler's consumption. and not for humans' consumption. And I guess back to the previous question a bit, one of these things these pages typically have is either a meta refresh or a JavaScript document write in order to take the surfer back to whatever their kind of main site is. And so these pages aren't trying to kind of sell you anything or do the type, phishing type things that kind of email spam does. They're really geared toward having links and keywords and things like that that are going to be searched for, which is kind of the push versus pull.
My general thought was, if you're going to be sleazy one way, why not be sleazy too?
Any more questions? Okay. Let's thank our speaker then.